let's be serious. Oh, I hope I didn't record that. Oh, I did. Okay, so anybody have any general questions on naming? It's fairly simple. I do want to comment that you will not always have a straight chain compound. So let's talk about what happens when you have to name things that are not straight chain. So we're going to talk about naming branched compounds. I know my writing is sloppy. I apologize. So as an example of this, we'll start simple and we'll start with our alkanes. And if we start with, let's say, pentane. Remember, the carbons are surrounded by hydrogens. I'm leaving them off for simplicity. Pentane, 5 carbons, alkane groups. Now, it is possible for us to have an additional carbon group. I'll put the H's in this case to help us see them all. If we had a carbon attached in place of a hydrogen on this carbon here. So the hydrogen that was originally here, now I've replaced that and I've attached a carbon in place of that. So now we have another issue to consider here. First issue, what is the functional group? Alkane. We haven't changed the functional group, but we have possibly changed the longest chain of carbon atoms present. Now in this case it ends up we did not. As a matter of fact, let me change this question. I know. Let's just put the C there. So for those of you who are struggling to erase the C and put a new C, you can draw a new one. Sorry for the complexity there. But when I do it in this way, notice that when we get to the question of what is the longest chain of carbons, which tells us the prefix to use, now we have several choices to make. Before, we just had the issue of numbering from left to right. So if I do my 1 indicating from that way or this way, that was simple enough. But now notice, if I start at this one, for example, and start numbering, I have another place to end. So this is one chain, this is another. Which of those is the longest? The top one. Okay. So that first issue is taken care of, the longest chain. Now, which end do we start from? Do we start numbering? The answer is the same answer as before. The end closest to the first functional group or branch is where we start numbering. Now, it turns out in this case that both of those directions, from here to there, which is the first branch, that would be carbon number 3. Or from here over that way, that would still be carbon number 3. So either direction, whichever direction we start numbering from, will both be a carbon group attached at carbon number 3. Do you understand that? So just like before when we used a number to indicate where the functional group was attached, here we're going to use a number indicating where the attachment is. Now this is the attachment. It is a carbon with 3 hydrogens. Now, because it has 1 carbon, we use meth. The suffix for an attachment of carbon groups is YL. I don't really know how to pronounce it. I guess ill. So this group is a methyl group. If it had 2 carbons attached, we would call it an ethyl group, propyl group, butyl group, pentyl group, hexyl group. In this case, it's a methyl group, so we call this compound 3-methyl. There's the branch. That's the attachment, the functional group. And it has 5 carbons in a chain, so it's 3-methyl pentane. So take a moment there to think that through. 3-methyl pentane. Here is the longest, here's the prefix of the longest chain. Here is the suffix of the chemical group, just like before. Here is the location of the attachment or functional group, and this is the identity of the functional group. Notice the difference. When that functional group was an alcohol group, OH, we changed the suffix. There was no need to put 3-hydroxyl pentanol. We would just put 3-pentanol. The suffix would take care of the functional group. But because the attachment and the suffix are the same, we have to have both of these names in place. Okay? Good? Try this. So looking at that, what functional group is present? Alkanes. What's the longest string of carbons? But not naming it. How many are in the longest chain? 6. Okay, so where do we start numbering? We could start numbering here. We could start numbering here. We could start numbering here. Which of those would be the longest? Well, from here to there, that's only 3. Definitely not it. There to there, 6. How about there to there? How many is that? 6. How about from here to there?
6.
How about from here to there?
6.
Which one do you choose?
Any of them?
Well, the first rule for choosing is we start numbering from the end closest to the branch. So which of those 3 can I eliminate? This one, definitely. So we're not going to consider that one. So we come over here. Now we pick one of these. Which one would you select?
The bottom one.
How about this one? It doesn't matter. It totally doesn't matter. And I'll show you why. I'm going to pause the video. I'll come back and get started. So it does not matter which one I start with. I'll start with this carbon, or excuse me, I'll start with this one just as a reference point because it's straight and it'll help us to count better. So if this is carbon number 1, the branch is on carbon number 2. So I put 2. What is the name of the branch? What is the name of this carbon group? Methyl. Good. And the longest chain has 6 carbons, hex, and it's an alkane group, hexane. Do you understand? You sure? Okay. Now try this one. I want you to draw, let's see. I'm going to write some names. We'll draw 3-methylhexane. I'd like you to draw that one for me. Okay? Sorry. Thank you. So I'm going to... Okay. So if you had drawn this correctly, you see the 6-carbon group. No double bonds, it's because it's an alkane. And then there's a methyl group on carbon number 3. So how about, should I put it here? How's that? Now some of you in class may have it written here. Would that be different? Exactly the same. Suppose you had it written here. Would that be different? It's exactly the same. Suppose you had it here. Is that different?
Nope.
Those are all the same. If you're not sure, imagine going back to the original black carbon I had drawn there and flipping it over from here over to the top. It would be that one with the blue. Or imagine picking this thing up off the page and flipping this end over to this side. Then that black carbon would be where the green one is. Or imagine flipping it and then rotating it up, and that would be where the red one is. They are exactly the same. We all good there? Okay. Let's go ahead and move forward to some new material. I wanted to take a second here to move. I'm going to take a moment to plug some study material. This is a link. I showed it to you guys in class yesterday, but when you're watching the video again, there's the entire link. You can scroll and see it for yourself. That's where the IB Chem Guide is, which is the curriculum. That's on the shared documents link. That's where I'm getting these headings from. Topic 10 is organic chem. So when you go study that, we're talking about topic 10. It's a very good study tool. Okay. Now the first thing we're going to talk about is what is called a homologous series. It's a very simple concept. I'll actually draw it up here. A homologous series is a set of compounds which differ in only one thing, and that is that each member of a series contains an additional carbon group. Excuse me, I can't spell. So, let me change my color here. So, for example, this is methane. The next member of the homologous series would be ethane. Notice the difference. One extra carbon group. The next member, propane. I'll leave the H's off to save time. The next member, butane, and on and on and on. That is a homologous series. You understand? Very simple. Homologous means same shape, or same structure, I guess you could say. So that's indicating that they are on the same shape. They're straight chain. They have the same groups. They have alkane groups here. The only difference is the number of carbons. Very simple concept. Okay? Now you are required to know A, what a homologous series is. And I've taken care of that. And a homologous series could be in a different functional group. For example, we could write a homologous series of alcohols. So as a matter of practice, I'd like to see if you could name this. This is a 1-carbon alcohol. What do we call that? Methanol. This is a 2-carbon alcohol. What do we call that? Ethanol. This is a 3-carbon alcohol. Be careful. What is the name of this? It is not propanol. It is 1-propanol. Is there another 3-carbon alcohol I could have drawn that was different than this? I could have put the OH here. What would it have been in that case? 2-propanol. Okay, so I'll go back to my sequence. What would this one be called? Not 4. There's no such thing as 4-propanol. 1-butanol, right? Well, sorry, 1-butanol. It's not, I said propanol, it's butanol. You understand why? Okay, so that's also a homologous series. I want to be clear. It doesn't have to be just alkanes. So let me go ahead and erase that alcohol because I'm still wanting to talk about the alkanes. So you are required to, in addition to know what a homologous series is, you are also required to know, some physical properties of these. So let me make this very simple. You are required to know boiling points. I'll just summarize it down to one simple physical property. Now you learned previously how to determine boiling points of substances. They are a function of intermolecular forces. Stronger forces, higher boiling points. What type of intermolecular forces did we study? Van der Waals, also called London dispersion. We studied hydrogen bonding and dipole-dipole. Agreed? Right?
Yeah.
Now, in these compounds, these alkanes, the only forces present are van der Waals. We call them London dispersion forces. It means the same thing. When you read the chem guide, they'll be called van der Waals. VDW, it's the same thing. Okay? So, how did we learn that London dispersion forces, van der Waals forces, change as the number of compounds the number of elements in the compound changes? Anybody remember that relationship? I'll rephrase it for you. How does the van der Waals or London dispersion forces of this first compound compare to the fourth compound I had drawn? Higher or lower? Okay, this is embarrassing. Okay, so as the number of electrons increases, the London dispersion forces, van der Waals forces, increase. Well, if the van der Waals forces increase, that means the boiling points increase. Okay, so the lowest van der Waals forces, like here in methane, would have the lowest boiling point of this series, and the boiling point would continue to rise in this series of 4. That would have the highest boiling point. Any questions on that? Okay. Now, when we add the issue of branching, for example, now this would not be a homologous series, what I'm about to draw, but I feel like I need to do this right now. It's a 5-carbon. There's pentane. Here's another compound with exactly the same, these two are exactly the same formulas. There are 5 carbons, so we say C5, and so the number of hydrogens is going to be 12. This one below is also C5H12. So if I ask you which one of those two has the stronger intermolecular forces, the van der Waals forces, they both have exactly the same number of electrons. So if that's true, what do we fall back upon? What do we compare in this case? Shape. Good. So if they're straight, they can pack more tightly. Agreed? So in this case, this one would have the higher boiling point than that one. You guys do remember that?
Yeah.
Okay. Good. Good. I'm just going to go ahead and continue. I'll edit it later. So anyway, back to the homologous series issue. They just differ in the number of carbons. Okay, you need to understand that boiling points can change. You can see a little chart I put here. This shows some of the alkanes. Here's their molar masses, which is an indication of how many elements are present